Okay, let's do another example. Now, up to now, the previous examples when we calculated the flux, they were just flat surfaces. Now, let's take a bent surface. This is X, Y, and Z. And let's say we have some charge over here, plus Q charge. And I will imagine a, let's say, a semisphere. Of radius r. Now just imagine a sphere. Now what will be the flux that goes through this sphere, semisphere? Now in this example, the strategy is basically the same. You just divide it into very small surface areas which are approximately flat and in which the electric field is constant. So you just take very small areas. Etc. Each one having, let's say, the magnitude of the area is ds, and we can just say that this is the ds vector at this point. It will be perpendicular to the surface. Of course, this ds vector will have a different direction in everywhere. So if you just take it, this is our sphere. If it's pointing in at this direction, at this point it will be pointing in that direction, at that point it will be pointing in that direction. It's constantly changing. But we know that since it's a sphere, it is always pointing in the radially outward direction. So this we can also write as ds, the area of that very small segment, in the r hat direction. This is the radially outward vector. Now we also have studied the electric field of the point charge, and we also know that the electric field of the point charge is 1 over 4 pi epsilon 0 q over r squared in the r hat direction. It's also radially outward. So at every point, although this ds vector is changing at every point on the surface of the sphere, it is always pointing in the same direction as the electric field. So E dot ds for every point on this sphere is equal to 1 over 4 pi epsilon 0 q over r squared ds. And since I'm considering the areas on this sphere, and the sphere has a radius r, for each one of these areas, this small r is nothing but large r. They are equal on the surface. So the flux would be 1 over 4 pi epsilon 0 q over r squared ds integrated over my surface. But integrated over my surface just means that since I have divided my surface into very small areas, I'm just summing over the contribution of each one of those areas. But since I'm integrating over the surface, r is just a constant. Q is a constant, 4 pi epsilon. They are anyway constants. So this is nothing but 1 over 4 pi epsilon 0 q over r squared times ds. Now this is nothing but the sum of the areas of each one of these small patches. And we know that we already know the area. This gives the total area of this hemisphere. And the total area of this hemisphere is q over r squared. Since I'm just considering half of the sphere, it is 2 pi r squared. This is q over 2 epsilon 0. Well, just taking a hemisphere or a full sphere, I mean, the derivation would be practically identical. The only defect is that this integral, if we had taken a full sphere, let's take a full sphere this time. Here I have some plus q charge. In this case, E dot ds. This would be equal to 1 over 4 pi epsilon 0 q over r squared times 4 pi r squared. And this will be q over epsilon 0. The only difference is that in this derivation, this integral, that is the total area of my sphere, of my surface, would be not 2 pi r squared, but 4 pi r squared. Just a notational change. Just to, this is a closed surface. Just to clarify that we are integrating over a closed surface, we just put a little circle on the integral side. This is not a line integral. This is an integral over a closed surface. This circle just means that it's an integral over a closed surface. Now, if you compare this result with, let's say, this one, and of course, there are the fluxes through completely different surfaces corresponding to completely different electric fields, but there is a fundamental difference between these two. Can you, if you look at this one, the flux, remember the flux was nothing but the electric field times the area. So if you have a larger area, it's kind of natural to expect that the area, the flux will be larger. So here we see that. The flux is proportional to the area that we choose. But here the flux doesn't depend on the area that we choose. It's kind of independent. Now, whether you choose a very small sphere or a huge sphere doesn't really make any difference here. The flux will be the same. Well, if you choose a very small sphere, of course the area is very small, but the electric field is huge. So these two effects, the smalling, if you reduce the area, the electric field is, you are also increasing the electric field. They somehow compensate each other. So independent of what is the area of the sphere, the flux that goes through the sphere is always the same. Now, if you think of it in terms of the number of field lines that goes through the surface, it makes more sense, because in our definition of the electric field lines, we said that they start from positive charges, they end at negative charges. So if you have a single charge, let's say, a single charge over here, we have all these field lines that are leaving this positive charge. If you take a small sphere, the number of field lines is nothing but the total number of field lines that leaves your positive charge. If you get a larger sphere, the number of field lines is still the same. So in fact, that is why we have this. The total flux that goes around this point charge is independent of the size of our surface, because you are basically counting how many field lines are leaving your charge. And they will, of course, go until infinity. Now, if you, keeping this in mind, you are basically counting the number of field lines that's leaving your charge. And in fact, this relation kind of tells you that you have to choose the number of lines to be equal to Q over epsilon 0. What do you think the flux would be in this case? Okay, we again have a sphere. But this time, I'm not putting the charge at the center. I'm putting the charge over here. What will be E dot ds? Nothing will change, because basically we are counting the number of field lines that is leaving my charge. This will again be Q over epsilon 0. Now let's, any questions on this one? If you have a point charge, if you take a sphere around this point charge, the flux through this sphere will be nothing but Q over epsilon 0. No. No, the electric field of a point charge is Q over R squared times 1 over 4 pi epsilon 0. This is the electric field magnitude. This is the flux. We are writing the flux. Now let's look at another example. I have a point charge, but this time I don't have a sphere. I just have some arbitrary shape, closed shape. E dot ds. This is equal to, again, Q over epsilon 0. Whatever the shape is, E dot ds just counts the number of field lines. And we have already seen that the number of field lines, the total number of field lines leaving a point charge is Q over epsilon 0. No matter which method you use to count the number of field lines, you should always get the same number of field lines. You can use a perfect sphere to count them, a perfect sphere with its center at the point of the charge to count them, or just some arbitrary closed shape to count them. The number of field lines is always the same, should be the same. Then if it will not be equal to Q over epsilon 0 because some of the field lines will be passing through that hole. Now suppose, now let's just consider another case where we don't have a single point charge, but many of them. Qi. Then I know that the total electric field will be nothing but the sum of the electric fields created by each one of these point charges. If I consider any closed surface around them of any shape, E dot ds would be equal to sum of EI dot ds. But we had already seen that for each point charge, this EI dot ds is nothing but Q over epsilon 0. Now let's do one more thing. Let's say that I have this charge, this mathematical shape. Rather than putting the point charge inside, I will put it outside. In this case, what will be E dot ds? Now remember one of your friend's comments. I mean, the flux can also change its sign. Now, if you have a closed surface like this one, any one of these, like this one, if you have a closed surface, what you are actually counting is the number of field lines that goes from inside to the outside. That is what you are counting. And for each charge inside, it's Q over epsilon 0. Now in this one, some of you said that it's changing, some of you said that it will be 0. Of course, some of them will pass through my closed surface. Some of them will not even touch it. What will be E dot ds? Remember, I am counting the number of field lines that is going out. If I have a field line that is going in, that counts as a field minus one field line going out. So let's see, let's follow this field line. for this field line, there is one that enters into my surface, that is -1 field lines going out, +1 going out. So the sum of the contribution of this field line is 0. It will be 0 for all the field lines. Since there is no charge inside, if there is an electric field line coming in, it has to go out. So the total number of field lines will again be 0. This is equal to 0. Now, if you go back to this example, let me change my surface. Let me imagine a surface like this. I have some charge distribution somewhere. Some of them are inside my closed surface, some of them are out of my surface. Now the total electric field is just the sum of the electric fields created by each one of these point charges. If I calculate the flux, the flux created by the total electric field, it is nothing but the fluxes created by each one of the point charges. Now, we had already seen that if my charge is inside, the total flux it creates is Q/ε0. Let me put a prime over there, meaning that I am summing only charges, sum over charges inside my surface. And we can just write this as the total charge enclosed by my surface divided by ε0. Enclosed. I will not rise the I only sum the charges inside my closed surface, not the ones outside. Because if I have charges outside, the field lines that they create just enter my region inside my surface and then leave it. They don't contribute to the net flux that goes through my surface. You just count them. Let's see, in this case, if they are all the same charge, I have 1, 2, 3, 4, 5, 6, 7, 8. We will do some examples, don't worry. So this is basically our result after all these discussions. We have E dot ds. If you take any closed surface, integrate the electric flux, calculate the flux that goes through that surface. The total flux that goes through that surface is equal to the total charge inside that surface divided by ε0. This is always true for any surfaces that you can imagine. Of course, restricted to electrostatics. Again, this surface that we are thinking over here is not a physical surface. It's not a surface that exists in reality. It is a surface, a mathematical surface that we just imagine. And whatever surface you imagine, this relation should be true. We can discuss it later on. Now let's discuss something else. Your friend had said that we had already been saying that we can always change the sign of ds. What happens then? I mean, you can just change the direction of your surface. ds goes to minus ds. So what happens to this relation? Now the question, let me rephrase the question. Suppose we have this charge distribution. Some charges somewhere. And we imagine a surface. I mean, some charges can even be outside. Let's say that the total number of charges outside is Q1, the charges inside is Q2. Now, since we have this freedom to choose the direction of our surface, so we can say that, okay, our surface, the outside can be in this direction. Let's call it ds1. Or outside can be this direction, ds2. And since they are both perpendicular to our surface, there is a sign difference between the two. Now, if we calculate the flux using the first choice, or if we calculate the flux using the second choice, they will, of course, differ by a sign difference. Now, phi1 is what we were always considering. We always had that in mind. The inside of the surface is clear, inside the sphere. And so this is equal to Q2 over epsilon 0. This is phi1. How can we apply Gauss's law to phi2? This is Gauss's law. How can we apply this law to the second choice of our orientation of the surface? What is Q outside? That's in fact the issue. I mean, you see, if you look at the Q enclosed, this is the charge inside the surface, whatever you define as the inside. If you have this shape, we usually tend to define this part as the inside, so we just count the charges over there. So that is the choice S1. But we are as well free to define this as the outside, this as the inside. So what happens to Q enclosed then? We have to count all the charges outside this surface, all of them. Now, phi2, what is the total charges outside that surface? No. It is minus Q2. Let's call it prime. No. Remember, universe is neutral. There's no charge in the universe. If you put a charge Q2 in this region, the total charge outside that region, the total of them have to be minus Q2. Q1 is only the ones that are in this region. We can also have charges at infinity, which we cannot show here. If you also take those charges into account, well, they are inside my surface for the second choice of the orientation of my surface. The total charge has to be minus Q2, so everything is consistent. Now, the important thing is you have to be consistent. As long as you are consistent, all these things, these freedoms you have, you can use them. And whether you choose this as your orientation of the surface or the other one as the orientation of your surface doesn't cause any problems as long as you are consistent. By choosing the sign of the yes, you are choosing what is outside and what is inside. And Q enclosed is the charge. Q enclosed is the charges inside the inside that you have defined. Just keep in mind. Okay, let's do some exercises, some examples. One of them we had already done. We started from a point charge and we calculated the total flux around the surface that goes around it. Now the question is, Starting from Gauss's law, can we derive Coulomb's law? How can we derive it? I mean, if we can derive this, we can say that Gauss's law and Coulomb's law, they are equivalent. They contain the same information. Yeah, I mean, by Coulomb's law, that's what I mean, the electric field corresponding to the Coulomb's law. How do we find the electric field from Coulomb's law? I have this point charge. Using Gauss's law, how can I determine the electric field? This is our system. So your friend is saying, is our system symmetric? And of course, what does it mean to be symmetric? I just imagine this is the universe. This is the only thing that exists. Plus, of course, a minus q charge at infinity. This is our universe. So is it symmetric? It is. I mean, since you have just a single point, I mean, whether you look at your point like this, or just lean like this, or, I don't know, just rotate around it and look at it like this, you'll see the same thing. The charge distribution is the same. That is what we call rotational symmetry. So if you take your system, rotate it around, everything looks the same. If the charge distribution looks the same, the electric field it creates should also look the same. So that's what we mean by the symmetry. Now, so let's just take this point and this point. Point A and point B. What can you say about the electric field at the point A and the electric field at the point B? What can you say about those two electric fields? They are at the same distance. Let's say this is at a distance r, this is at a distance r. Well, I can just, I mean, since we said that we have this rotational symmetry, if we rotate our system, nothing should change. I can just take my system, rotate it such that point A comes to the point B, and nothing should have changed. That tells me that their magnitudes should be the same. What can you say about their direction? Again, you should always think that if you rotate point A to point B, including the direction of the vector, electric vector at the point A, when it comes to the point B, it should overlap with the electric vector at point B. So your friend is saying, okay, so the electric field at point A might be looking in this direction, and then the electric field at the point B will be looking in this direction. So is this your claim? So you are claiming that the electric field is pointing inside the screen. Okay, so your friend is saying that the electric field is pointing inside the screen, also here is pointing inside the screen. Right? So as you rotate the point A, this is your vector at point A. As you rotate it to point B, they overlap. This is what you claim. What about not the point A, but let's just imagine a point just out of the screen, just in front, here, this point, and this point, these 2 points. What will be the direction of the electric field at these 2 points? So you are saying that on the screen they are pointing inside. So if the point B was here, it's pointing inside the screen. So if you just come here, it is pointing towards you. So when did they change their sign? I mean, here it's pointing like this. There it's pointing like this. Somewhere they should change their sign, no? So this kind of doesn't really work. Well, I mean, let's not take too long. If you just test this one, electric fields that are pointing radially outward. Now, if you look at the previous one, we will see cases where we will have such electric fields, not radially outward, or we will even see electric fields that have such a behavior. They will make circles, closed circles, but that is not in electrostatics. Electric fields, remember, they have to start from the positive charge. They cannot be just in this direction. There's no way you can connect it to this positive charge. So the only way to draw electric field lines that start from the positive charge and that have this rotational symmetry everywhere is to have them pointing radially outward. This is the electric field over there, etc. I am on the sphere. If I'm at the same distance from my point charge Q, the magnitude of the electric field is the same everywhere because of this rotational symmetry. It looks the same no matter how I rotate my system. Furthermore, they have to be pointing radially outward. This is an information that you have to deduce before using the Gauss law. Because let's try to apply the Gauss law to this surface, this imaginary mathematical surface, E dot ds. This is equal to, let's use the cosine definition of the scalar product, the magnitude of the electric field times ds times what is the angle between the area vector and the electric field. It is 0 because we had already said that the electric field is pointing radially outward. It's in the same direction. Electric field is already perpendicular to the surface. That means it's in the same direction as my surface vector. So cosine of 0 integrated over this closed surface. Now, we had already concluded that the electric field on this surface have to have the same magnitude no matter where I am. Now, in this step, we use the fact that we had already determined the direction of the electric field. It has to be radially outward. Now we will be using the fact that we have already concluded that the electric field on this surface should have the same magnitude everywhere. If it has the same magnitude everywhere on the surface, this is just a constant which I can just take out of the integral. Integral of ds. But the integral of ds is nothing but the total surface area of my sphere. And from Gauss's law, I know that this has to be equal to Q over epsilon 0. Or the magnitude of the electric field have to be 1 over 4 pi epsilon 0 Q over r squared. We already know the direction. The electric field vector is E in the radial direction, Q over r squared in the r hat direction. Now, there are a few important steps here before even we use the Gauss law. We first had to determine certain properties of the electric field using, let's say, symmetry. In this case, we have this rotational symmetry. So the electric field had to be pointing radially outward from my charge. And on a sphere whose center is at my charge, the magnitude has to be the same. Those two things we have to determine before applying the Gauss's law. And using those two properties, we could first calculate the scalar product in terms of the unknown, the magnitude of the electric field. And since we already know that the magnitude of the electric field on our so-called Gauss surface is constant, we could just take it out of the integral. And what remains inside the integral is something that we can evaluate. R is the radius of the sphere. This one. This r hat vector. R hat vector is this vector. I'm not summing these vectors. You see, here I'm not summing the area vectors. I'm summing the magnitudes of the areas. You cannot find any surface along which the electric field is constant. Gauss's law is still valid for the system, but it's not of practical use. You cannot start from the Gauss law and obtain the dipole formula. But let's stick with this one first. To the statement of the Gauss law. This is what we have, the Gauss law. It just tells us that if you imagine any mathematical closed surface, anything, and if you calculate the flux that goes through that mathematical surface, the total flux have to be equal to the total charge enclosed divided by epsilon 0, independent of the, let's say, the shape of this surface. As long as the enclosed charge is fixed, you can just change the shape of the surface. Nevertheless, the value of this integral will not change. This is the Gauss law. No, it doesn't say anything. The electric field lines need not be perpendicular to our surface. Whatever the surface is, this still holds. Now, in this example, we know that Gauss's law holds for any surface. I don't have to choose this particular sphere. I can choose any complicated surface that you can imagine. Gauss's law will be valid. But it will also be valid for this surface. This is a sphere whose center is at my charge. And if the Gauss law is valid also for this surface, then the electric field should have this form. Well, I could have started and studied this other surface. But in this case, since I wouldn't be able to simplify my expressions, I wouldn't be able to drive any other conclusion. I wouldn't be able to say this. Any questions on the point charge? We will do an example. Questions on the point charge? Okay, nice. Let's discuss that one first, and then we will discuss your question. Okay. I think last week we were also discussing the conductors, and we said that inside the conductor you cannot have any electric field. You cannot have any net charge inside the conductor. Now let's prove the same thing using the Gauss's law. I will use the fact that inside the conductor, E is equal to 0. And ask the question, is it possible to have a net charge inside a conductor? Let's imagine that I have this conductor, and here I put some positive charge. Is it possible? Let's apply the Gauss Law. I can just imagine any surface that encloses this charge, any surface, and let's calculate E dot ds on this surface. What is E dot ds on this surface? My surface is inside the conductor, remember? So since my surface is inside the conductor, everywhere on my surface, electric field is 0. So this integral is 0. But Gauss' law tells me that this has to be equal to Q over epsilon 0. But this tells me that Q has to be equal to 0. Inside the conductor, I cannot have any charge. Let's do another example. Now, in this example, we said that our previous explanation was that if you try to put some positive charge, let's say, since the electrons will be free to move, electrons will just come on this positive charge and it will cancel it. And all the electrons, if one electron moves, it leaves a positive charge where it left, but some other electron just comes there and it will cancel, neutralize that one until we have some positive charge on the surface and no charge inside. But we can prevent the electrons to go to the positive charge. We can isolate the positive charge inside the conductor. We can just imagine that we have a conductor. Inside we create a hole, again of arbitrary shape, and put some positive charge here. What can we say? Now let's take this such a Gauss surface inside my conductor. We will do the same thing. Just imagine this surface inside the conductor. E dot ds. What is the electric field inside the conductor on the surface? Electric field is 0. So this integral is 0. But again, from Gauss' law, we know that this is equal to Q enclosed divided by epsilon 0, or the enclosed charge have to be equal to 0. How can this happen? Now, I can put one charge inside the cavity in the conductor, nothing will be touching it. So this positive charge is there, it will stay there. But the total charge inside this conductor should still be 0. A bit louder. Well, this is a positive charge, this is a conductor, so the negative charges are free to move. Negative charges will move towards our conductor. So we will have negative charges over here and positive charges on the outside of my conductor. And the Q enclosed is nothing but plus Q that we had put plus the induced charge in the surface. This should be equal to 0. So this tells me that the induced charge on the inner surface of the conductor should be equal to minus Q. Well, we are always assuming that the electric fields we have are reasonably small. Of course, the total, I mean, we are basically dealing with idealized cases in which the conductors have infinitely many positive charges and infinitely many negative charges. Sure, sure. I mean, when you reach that limit in any way, the electric fields would create such a great forces that it will just break up everything. You cannot create this configuration with such a large charge. Questions? Nothing will change. E dot ds will still be q over epsilon 0. And it will still be valid, but I will not be able to extract the electric field using that surface. Now, in the next hour, we will start with, let's say, an infinitely long wire. With a linear charge density lambda, charge per unit length. And we will calculate the electric field. Question before you leave? Sure. I mean, if you draw the electric field lines in this case, we will have electric field lines moving somewhat like this, and no electric field inside the conductor, and then we will get some electric fields outside. There is no electric field line inside the conductor. There is no electric field line inside the conductor. The electric field lines start at this positive charge, terminate at the negative charges on the inner surface, and then they start at the positive charges on the outer surface and go to infinity. Okay, a 15-minute break. Have a coffee.